Right, welcome back. What I want to look at today is audio frequency power amplifiers. Excuse me a moment. Now, in an audio frequency power amplifier, the main considerations are the output power and the efficiency. So you need to look at making your amplifier as efficient as possible. There will always be some losses, but the idea here is to minimize the losses. Okay. Now, if an appreciable output power is required, a large amplitude input signal is required. In order to obtain large swings of output current and output voltage. Okay. Now, sorry about that. The transistor used in a power amplifier must be chosen and biased so that its maximum current, voltage and power ratings are not exceeded when the desired output power is developed. What we're saying here is simply that you need to make sure that the transistor that you're going to use can handle the output power that you want to draw from your transistor. There's no point having a transistor that delivers 2 watts when you are actually looking for 10 watts. Okay, that simply means that you will overdrive the transistor and it would be completely useless to you because it will break down. Okay, so be aware of that. Now, the ratings figures of a particular transistor are available from manufacturer's data sheet. Now, if you go into buy a transistor, now one time we would be able to go into Maplins and buy transistors, but now you can probably buy those now online. But remember that if you're buying online, that you're sorry about that. That your data sheet, in respect of the manufacturers and its handling capacity to handle the current demand and provide the required power output, will be on your data sheet. So you'll need to look for 1, the transistor that you're looking for, 2, will it give you the power rating that you required, 3, the voltage that it can handle. Okay. Now, for the maximum power to be delivered by a power amplifier to its load without exceeding a predetermined distortion level, the transistor must work within a particular value of load impedance known as the optimum load. So this is the optimum load that you can drive or apply to your given circuit in order to get the maximum power and efficiency from your transistor. Excuse me. Now, power amplifiers using discrete components are either single-ended, i.e. uses a single output transistor to deliver the output power to the load, or 2 transistors may be connected in what is known as push-pull system. Now, I'm not going to go into the depth of each one in turn, but I'm just going to give you a rough outline as to how these can be used and how they would look. But for you to acquire a bit more information and knowledge, you need to look up the system for yourselves as in regards to push-pull and connecting of transistors in a particular mode, especially if you're looking at common base or common emitter. Okay, so those are the things you need to look up and do research on for yourselves. That will widen your knowledge for your own benefit and allow you to understand a bit more as to what's being said. Okay. Now, in addition, there is integrated circuits available for power amplifiers capable of providing several watts of power, of output power, and much more. Now, several watts of output power. Now, we have only used this as a simple example, but of course you can get massive watts of power if you wanted to by using amplification, especially where you come into using op amps, because op amps has a very high gain and that needs to be controlled. Okay, and you can get a massive gain by using operational amplifiers. Okay. Now here, the single-ended power amplifier. The output transistor of a single-ended power amplifier should work into its optimum load impedance. Now here again we're talking about optimum load impedance. This is the load which will allow you to have maximum power with minimum loss transferred into your load, whether that load be a light bulb, whether it's a speaker, or whether it's something else that you need to drive. Okay. This will rarely be the case, so transformer coupling is normally used. Okay. Now what this talking about in regards to transformer coupling is that we're using a transformer for the output stage in this particular case. Okay. Now transformer coupling also reduces the DC power lost in the circuit because the transformer primary winding usually has a low DC resistance. Now the turns ratio equals N equals N1 over N2. That's the turns in the primary, respective turns in the secondary. So N1 would be your primary, N2 would be your secondary. And that will give you the turns ratio in respect of your transformer, which will give you the relevant output for maximum transfer of power. So the turns ratio equals N equals N1 over N2 of the output transformer is chosen to transform the actual load RL into the optimum load R-L. Okay. This represents the transistor load in order to develop the output of the transistor. So here we're saying that RL represents the transistor load. Okay. And here we're looking at N will equals RL over RL, R dash L over RL, square rooted, of course. Okay, and this would be, that will give you the number of turns you need for your transformer. And again here, let's go back here. And here you can see that we're talking about RL here and in respect of these two here. Okay. And that's what we have here. Okay. Now, the stabilization of a transistor amplifier is best achieved by means of the potential divider bias circuits. But to minimize the DC power losses, and remember P equals I squared R in regards to power losses for DC. Okay. Now, the emitter resistance should be low. It could be as small as 1 ohm resistance. Now again, when we talk about the emitter, we're talking about the emitter in respect of the transistor. Okay? And you'll see where that comes into play further on as we move into this a little bit more. Okay? Now, when such a low value of emitter resistance is used, the resistor is not decoupled because the required capacitance value would be very high. And decoupling, simply now, this is something that you will need to do a little research on for yourself, so you can see where decoupling comes into in regards to a transistor circuit. Okay, as that again is a piece of work all by itself, but do some groundwork first, okay, so you can get the grasp of where the capacitors will be into the circuits, how they're used, and the various types of capacitors that is available, such as polyester, electrolytic types, etc., etc. Okay. Now, types of capacitors is already on my channel, so, and it's listed already there, so feel free to look that up and see what you may learn from that. Okay. Amplifiers with a power output of several watts and a collector current of several amperes, the emitter resistance may sometimes be omitted. So, all we're doing here is purely as an example of several watt amperes, okay? Okay, so it's a small amplifier, nothing large. Now again, just to recap, amplifiers with a power output of several watts and a collector current of several amperes, the emitter resistance may sometimes be omitted. Okay, and you'll see where that comes in a little bit later on when you begin to do the diagrams. Now, draw out the diagrams for yourselves. Okay, do not just take it as read. Okay, you will not learn all of it from just going through the video. Now a power amplifier is a converter of DC power taken from the collector power. Collector power supply into AC power delivered to the load. Okay. So here we're simply saying that we come off as DC, but when it's feeding the load, it becomes AC by the action of the collector or transistor. Now the most important thing about the transistor is not its power gain, but the efficiency of the power conversion in AC delivered to the load. Okay, and this is where we need our transistor to be highly efficient and to make sure that we get the maximum power transfer into our load based upon the current and the voltage that we have been using, or which has been applied to the transistor. Okay. And here we have our circuit. Okay. Now with these diagrams, draw them out. Okay. And here you can see that the output is taken from the transformer, and that is all RL here. Okay. And that is R1 and R2. Okay. Here these becomes, you can, well, I normally refer to these here as a potential dividers, because they will limit the voltage. They will create a voltage drop across that circuit, which will be applicable, which will then be applied to the base of the transistor, and normally it's about 0.7 volts approximately. Okay, but here we have our output RL. Okay, and here we have R3, which is the emitter resistor. Okay. Here is your VC supply. That would be the positive rail, that would be your negative rail or ground if it's connected as such. Okay. If you're using an oscilloscope, you can actually see, you normally connect this to ground to get a different sinusoidal waveform or a waveform to see what the effect would be, and you would do that purely for the experience of seeing the effects of changing or even removing this resistor. Okay. And here this is a single-ended power amplifier, undecoupled. It has no decoupling capacitor. And here you see that the coupling capacitor will normally come between here and here. Okay, so whether you come this side and down doesn't matter, but you'll have a decoupling capacitor which would be connected to here, drop down, and would bring this down to here. In short term, it's almost bypassing the resistor, because the capacitor will have a different effect to DC than the resistor will. Okay. Let me just go back up, make sure everything is in. Okay. Now remember to go back to the work so you can see what we've been talked about, what is being said. Okay. Now here we need to look at calculation of divided chain, and you will remember that earlier when you go back, I was trying to tell you about R1 and R2. That becomes your divided chain. Let us look at how the divider chain works. We will consider that we need to calculate suitable values for R1 and R2. And you will notice that I mentioned R1 and R2 previously before. And here we have R1 and R2. Okay? For R1 and R2. Now let us assume the divider is to feed 2 volts to the base of a transistor. Now the transistor base current is about 0.1 milliamps and the supply rail is 10 volts. So notice here we have the given amps, we have the voltage, okay? First we need to work at the circuit and include on the circuit all known voltages that will be required and currents. Okay? So the 2 volt drop across R2 is given, and the 8 volts follows from the knowledge that in a series circuit the total voltage must add up to the total supply voltage. So if we know that the voltage drop is 2 volts and we've been told that it is 10 volts and we have a supply voltage of 10 volts, we therefore know that 2 from 10 leaves 8. We then know that 2 from 10 leaves 8. So therefore the 2 volt drop across R2 is given, and the 8 volt follows from the knowledge that in a series circuit the total voltage must add up to the total supply voltage. The voltage across R1 must therefore be 8 volts. That is done by Ohm's law deduction. Okay, simple as that. We have a transistor which will be fed from a divider chain. The load on the divider chain will be the base current to the transistor. Now we have decided we want a current of 0.1 milliamps to arrive at the base of the transistor. But if 0.1 is applied to the circuit, we have to consider the current loss in each resistor. Therefore, the current arriving at the base of the transistor would be less than 0.1 milliamps. So again, here you can see we need to take certain things into consideration and into account. Okay? Now, to ensure we get the correct balance, we use what is called the 10 times rule and add 1 to that for the top resistor R1. Add 1 to the 10. Now, as we have said, we wish to pass a current of 0.1 milliamps. Applying the 10 times rule for the current, I need to pass down the chain. Therefore, 0.1 times 10 to the minus 3 times 10 equals 1 milliamp. So therefore, from 0.1 milliamp, it's going to give me to 1 milliamp. We now need to multiply by 11. 0.1 times 10 to the minus 3 times 11 equals 1.1 milliamps. So you can see that we are acquiring the current value that we need to take into account in regards to the resistors that will be in the circuit. Okay. Now, as previously stated, we know there is 8 volts across R1. We know there is 2 volts across R2. Okay. So, to calculate resistors, which will give us the values of R1 and R2, which will allow a current of 1.1 milliamp to flow when the resistors are in the chain. To do this, we use Ohm's law. And for R1 equals 8 over 1.1 times 10 to the minus 3 equals 7,272.72 ohms. For R2 equals 2 over 1 times 10 to the minus 3 equals 2,000 ohms. Okay, now remember that this would simply be 2 kilo ohms, 7.27 kilo ohms. Okay. What happens if there is insufficient current down the chain, R1 and R2? The voltage at the output will fall appreciably when the load is connected. Remember, the current to the load comes down R1 via the supply rail. The voltage at the output will fall appreciably when the load is connected. Remember, the current to the load comes down R1 via the supply rail. Any change in current demand will cause a voltage drop across R1. What if we have too much current down R1 and R2? This is excellent as far as stability of load voltage is concerned. Any change in current required by the load will be negligible in relation to the large drain current, and voltage variations across R1 will be quite insignificant. Okay? So in short term, say, in this case, it would benefit by having a larger current, which will cause a developed voltage across the load. Okay. But there is one major problem with this. The heavy current drain in the divider chain puts a drain on battery life, therefore increasing extremely the cost of batteries and increasing the cost of power packs. There's a number of things you then have to take into account. Okay? Now there is another reason for not having too much current down the chain. If a signal is applied to the input of the rail and the resistors are calculated to pass a current, then the chances are the signal applied would be shunted across the low resistance and would be short circuited. So none or little amplification of the signal would take place. Again, just make sure we have all this in, okay? And again, don't forget to go back and look back at what's been said in regards to this work, okay? Do some research for yourselves, some groundwork. Okay, now here, what I've done here is to look at now an example, okay? So example of using a voltage divider chain. Now I've made this large, so the idea here is to provide you with detail. And using a voltage divider chain, that's what it says there, okay? So here, 9 volts rail, R1, R2 potential dividers, electrolytic type capacitor, okay, your input, NPN type transistor, okay, and this is your emitter resistor, okay, R3. The lamp here is acting as your collector load, okay, in this case, okay. Now here's where you would input your signal, okay, and your capacitor would then remove any unwanted responses. Now ground or negative, okay, simply that. On your breadboard there would be something like that, okay. Now sorry about that. Now let me just pull back a little bit from here because I want to bring this into play if I can. Okay, this is your breadboard, which is what these circuits will be built onto. Okay, so you can use these breadboards, and they will actually allow you to build these circuits. The interesting thing about building these circuits on type breadboards like this is that you can actually dismantle them and use that again and again and again. Okay, and then you could add to these building blocks, which allow you to build even bigger circuits and to see how it works. Okay. Right, thank you. So let me just go up, make sure we have everything in. Okay. Okay. And here, what I'm now going to look at is using a collector to base resistor. Okay. Now here's our VCC supply rail. Okay. Collector to base resistor. This is your collector to base resistor. Okay. What this does here, this provides a feed here. So what this does, providing there is a given demand at that point in time in regards to your signal, this will cause the base of the transistor to switch on slowly, okay, and then allowing current to flow through, or I should say electrons to flow through your lamp, bringing your light on. Okay. But remember that this light only comes on when the base of the transistor has been triggered and it's switched on. Okay, nothing else will happen there, and this acts as a controlling device. Again here, input points. Okay, input points. Yeah. And using this type of circuit allows for better stabilization. Okay. Now using a collector to base resistor allows stabilization to take place in the following way. If the collector current should try to increase, the voltage at A would decrease. So let's look at the voltage at A. And that's where we're talking about. The voltage at A would decrease. Okay. So here we have the voltage A would decrease. Now, this means there would be less voltage driving current through the base of the transistor via RB. And when you look back at the diagram, you'll see where RB is. Okay, you can do that for yourself. This caused a fall in the base current, causing a reduction in electron flow through the transistor, thereby reducing the current at the collector. So this actually acts as a means of controlling the current to the base. And if you try to increase the voltage, the demand at A, then you reduce the current. That gives you your controlling device. Okay. Now, when you actually put these circuits on the breadboard, and you can actually play around with them, and you can change the value of the resistors to see what happens. You can put a resistor in place of the lamp, or you might want to put an LED in place of the lamp and see what effect that would have. Okay, and you can change the value of this resistor here to see what changes. By changing that value, what effect would it have on this base current, and you can see how it changes it and causes your lamp to be dimmer or even goes brighter in some cases, again depending on the load. So let's just make sure we have it all in. Okay, thank you. Let's go back to recap. Just recapping now. Okay, again, thank you. Okay. Okay. Right. Getting stable direct current bias. You have a diagram of the basic amplifiers, and as previously mentioned, the need for stabilization. The divider rail which may supply the base biasing voltage current is to ensure the collector voltage stays near the mid-rail voltage. Variation occurs when the gain of the circuit varies from some reason, for some reason, possibly an increase in current or temperature. If the gain in a transistor circuit increases, then the collector current increases and the collector voltage falls. Now, if this happens, the situation is restored by decreasing the base current. Okay? Using an emitter resistor. Using an emitter resistor, taking into account stabilization, if the collector current should try to increase, the voltage at A would increase, leaving less voltage across RB. This would decrease the base current and so help to stop the original increase in collector current, IC. Okay. Now again, you cannot do this in one go. You have to look at it and read it and do some additional research for yourselves. Look at how transistors are connected up in their respective wiring diagrams, etc. Now the emitter resistor provides feedback if it is required. If it is required, if negative feedback is not required, then the emitter resistor is decoupled. So we can use the emitter resistor to provide feedback if we so wish. Okay, that allows you to control the input current or signal to the transistor, and it allows a consistent control. When the collector current tries to increase, that is if you try to draw more current from the collector or a fault should develop, a short circuit, there would be an increase of voltage at A. And again, look back at the diagram we just looked at earlier. Okay, as the transistor became fully saturated, this would cause a drain on the rail voltage and current via the base and RB. As the rail voltage current drops, this reduces the voltage across RB, that is the voltage available to RB, reducing the current to the base. The transistor returns to a high base impedance or become less saturated, allowing the transistor to switch off, thereby reducing the increase in current at IC. Emitter resistor diagram shown below. Okay. And again, looking at what we've just said, this is not just showing you how it has affected your circuit. Okay, and RB here in this case here is 47k, and that is controlling the current to the base of your transistor. Okay, and remember here you will just be inputting your signal, and your signal may come from a signal generator or whatever you decide to input, but this would allow you to control the current at the base. Now the following is a divided chain circuit showing the values of R1 and R2. R1 and R2 are the transistor base current divided chain. Now this is used to determine the current to be delivered to the base of the transistor in order to switch the transistor on without saturating the transistor. It is important that you first determine the voltage which is to appear at the base of the transistor. This will normally be about 2 volts. If the VCC supply is 10 volts, then 10 minus 2 equals 8 volts. You will have 8 volts being dropped across the R1 and R2 resistor. Now, we have just looked at this earlier. Okay, so the principle is still the same. The voltage at the base of the transistor is therefore 2 volts, which is the voltage across R2. Okay. Now again here, we're simply applying the calculations which we did earlier. Okay, just that we're doing it now for a different amplifier, but the principle of calculating the R1 and R2 is still the same. Okay. Now the load is the transistor base current. This current will be 0.1 milliamps, not 0.1 milliamps, my apologies. Adopting the 10 times rule, and the current draw down the chain should be about 1 milliamp. Allow 11 times rule for R1, current passing will be 1.1 milliamps. Now we know this because we've calculated this previously, so look back if you need to see what has been done. Okay. Values of R1 and R2. R1 equals 8, etc. 7.27 kiloohms. Okay, and 2 kiloohms. Now you'll see this here has been applied, so I've used the same resistors throughout the circuits. Okay, it made calculations a lot easier. Let me just follow this to make sure that we have everything on. Okay. Now here I'm looking at the various connections of transistors. Okay, here we have common base. Okay, common base transistor, and here we have common base transistor connections has a short circuit current gain. Okay, and the gain is less than unity, about 0.992. A low input impedance of about 50 ohms, okay, etc., etc. And here we have the common emitter, okay, common emitter. And here you have common emitter stages are biased so that the transistor is current gain operated. The input impedance is in the region of 100 to 2000 ohms, while the output impedance is about 10 to 30 kilo ohms. Okay. And here you have common collector or common collector or emitter follower circuit. Okay. And that is your input stages here. Okay. Output stages. Okay. And here I'm just simply saying that this connection has a high impedance, a low output impedance, and a voltage gain of less than unity. The main use of the emitter follower is as a power amplifying device that can be conveniently connected between a high impedance source and a low impedance load. They are useful as buffer amplifiers. Okay. And here I'm just showing you the calculations that we did for in respect of the 11 times rule and the values, how it was done. I like to show the principles of calculations so you can see what needs to be done. Okay. There you are again. Okay. Let's just make sure we get this all in. Okay, now please try and answer the questions. Okay. And you can see here that I've actually given you calculate the value for R1 and R2 when the voltage is 18 volts on the rail. Okay. And you can look at using the same values of resistors in place. Okay, that will be it for now. Thank you for your time, and I hope you found this useful and informative. And I've put in a simple diagram of an audio power amplifier circuit diagram, purely just show how this can be done. Now you can build these things again, as I said, on the breadboards. Okay, you'll be surprised how they actually work and how proficient they can become. Now there was Maplin's one time that I used to shop at, no longer in existence. Radio Shack used to be available as well. All those companies and so forth has gone, and quite a number of electronic shops in my time was available. But you guys will need to find your own input stages or your component places where they will sell electronics. And you'll find that when you begin to play with this stuff and it actually works, it's a very, very pleasing feeling. Okay, that'll be it for today. Thank you, and again, until next time, bye bye for now. Thank you.